All right. Curvilinear coordinates. Well, first you got spherical polar coordinates, which we'll talk about in the last. And before that, we'll in fact talk about cylindrical coordinates. So all of this, I will just skip that, and I'll just go straight to the cylindrical coordinates. Wait a second, it's loading. Yeah, it's gonna take some time. Well, yeah, some problems. All that I'll do later. First, cylindrical coordinates. Okay, so they're using phi as this angle. I'm using it as theta. Both mean the same thing. Then they are defining these unit vectors. I to define the unit vectors, but more graphically. So you can see what these unit vectors actually are. Uh, Theta hat is the unit vector along which your point moves if you just increase the theta without changing your r and z coordinate. And similarly, r hat is the direction in which your point moves if you just increase your r, if you just nudge it by dr, right? Similarly, z hat, but you know what z hat is, right? Then there's the cylindrical to Cartesian coordinate conversion, which is given by this thing: x equal to r cosine theta, y equal to r sine theta. No big deal. You can definitely understand that. And this r vector, usually I use small r for the position vector, but in this case, our r vector is just x, y, comma 0. That is it. It's the only the xy projection of our complete uh, radial vector, or what do we call it? The position vector. Yeah, so it's just the xy projection of that thing. Okay. Uh, right. That's all that, the basic stuff, and then he just goes straight into these formulae. So you got the gradient, divergence, curl, and Laplacian. Well, this Laplacian thing, I don't know where I'm going to use that, so I didn't actually derive the thing, right? I only did gradient and divergence and curl. So I'm going to show the derivation first. Okay, so first the derivation for gradient, which is very easy in fact. Once again, you just have to figure out um, a vector such that you have the f is equal to that vector dot dr vector, right? And when I say dr vector, I mean like the capital R vector, right? Basically this thing, and this should happen for all direction in which you will put this dr vector, right? So our dr vector is given by this thing: r hat dr plus theta hat r d theta plus z hat dz. So why r d theta? Because just d theta is not a length, so that's why this times r d theta, and basically that is the length moved when you change theta by d theta. So yeah, I mean, going from there to there, the amount of length that you covered is just r d theta, and that's in this direction theta hat. Of course, it's supposed to be curving, but then to a first degree approximation, good enough, right? And since we're dealing with differentials, I think it is equal to that, right? Okay, so dr vector, you can write it like this thing, right? And of course, it depends on what's the, what's the ratio of dr, d theta, dz, right? Depending on that ratio, you can figure out what's the direction of this thing. Where is this pointing? So we can figure out what r hat is. But yeah, like, doesn't matter what these things are, the multivariable chain rule still holds, and then you can write df equal to this gradient dotted with dr vector for any kind of uh, ratio of our dr, r, d theta, and dz. So basically for any r hat, you can write this equation, which means that, yeah, like, this thing is our gradient, right? Yeah, I mean, if this is the gradient, then you can do this thing for uh, every r hat. That basically means it is the gradient. Yeah, there's no contradiction anywhere. So that's how we define it, right? Okay, then you got divergence. So divergence is a little complicated. Um, you have to do the flux upon volume thing, right? The way we defined divergence initially, that was just a flux upon volume, right? Or we call it like partial flux upon partial volume, whatever. That thing you have to do it. But then what will be our volume so that we can, do it easiest way. So this is the volume that I've chosen. So what's happening is that these two lines, well, they look very parallel, but they are actually intersecting some very far point away, and they make angle d theta between them, right? Okay, and that's why this length is smaller than this length. And this length is of course an arc. It's an arc of a circle centered at origin with radius small r. This would be with radius small r plus dr. That's why this arc length is just small r plus dr, that times of d theta. This thing is dz, right? So it's like a prism of this thing, of this weird base. Yeah. So what's the flux because of these two surfaces? This surface and this surface, with the areas r d theta dz, and this one also, like, okay, this has r plus dr d theta dz, right? So what's the flux because of those two surfaces? That's just just this difference, right? And when I say it is this difference, it's like an approximation to first to some degree, right? Because of course it's supposed to be an integral of this difference, in fact, right? ur of r plus dr minus ur of r. But that means like you take some point of this thing, and then you take the similar point, I don't know, I should say projected to that surface or something like that, right? So you take that point, and then you figure out what's the ur values at those 2 points, subtract them, and then this difference is almost the same everywhere, because it's a small volume we're talking about, so it's the same, right? It changes, yes, but not so much. So yeah, this difference is just a partial ur upon partial r dr, right? And that's kind of constant. So yeah, you just do that thing. And of course, to get this difference, what you should do is you should first of all separate this r plus dr by distribution. So you got r d theta dz ur, and over here you got r d theta dz ur, and then you can do this different stuff. But what about the dr that we separated? So you got this thing as well, right? ur dr d theta dz. But look what dv is. So the volume of this thing is just r d theta dr dz, right? I mean, just multiply these things. It's almost like a cube, isn't it? So when you will divide this thing by our dv, what you will get is this first term, ur upon r plus partial ur upon partial r. And similarly, you do for other surfaces. So you do this for this surface, then yeah, like it's the flux because of surface is perpendicular to theta hat, right? That's why phi theta hat. Okay, so you got some flux from this surface and some flux from that surface. Yes, theta hat is changing as we go from this surface to that surface, but whatever, right? The flux will still be just this area times times our u theta thing, right? Yeah, so this got this area is like dr dz for this one. Then you got u sub theta of theta plus d theta, because yeah, like this surface has its theta coordinate as theta plus d theta. Its r and z are changing, so yes, it's not the same value everywhere, right? U theta doesn't have the same value everywhere, but just take the value at some certain point and take this same and take the value at the corresponding point on this surface, subtract that, and that difference remains almost constant, right? So you can still do it the same way, right? Pretend as if it was the same value everywhere. Yeah, and moreover, it is such a small volume that you can kind of pretend. So taking this difference and then yeah, converting this to partial u theta upon partial theta times d theta, right? That's what this difference would be, and that times of these guys, which was just dr dz, right? That's what this thing will be. So this divided by dv, that would just be this term. So it's like partial u theta upon r partial theta. So r d theta, if you remember that correctly, that was somewhere over here, right? Yeah, that's this length. So apart from this thing, this looks a lot like you just did del dot u directly. So like, okay, I'll explain what I mean by that. So you need a new definition of del for that, and which I will explain. For now, just know that this is our formula that we finally got by doing this little derivation. Let's go to the next thing, curl. This is hard to derive directly, um, right? Because it has three components, and this also had three components, but then it was easier because it was just like, you know, flux upon volume. This thing over here, you have to figure out an integral. So every integral will have like four calculations, right? And then divide that by area, and each area will be different. So you have to do these calculations individually. But whatever, let's just start. So first thing, we'll consider this loop, and of course this is like just the boundary. This surface is what you are supposed to be considering. Yeah, this surface, it has its area vector pointing in the r hat direction everywhere. This r d theta length, that is an arc length about the origin. Of course, this thing is along the z coordinate. I mean, this surface basically is just, this surface, right? Yeah, just separated from the whole cube thing. Is that a cube? I don't know. So you got this surface, and we are going to move in this along this boundary like this, and then applying the right hand rule, the area vector would point in this direction, and the area vector, like its unit vector, would just be r hat. So yeah, and of course r hat changes on this surface everywhere. It's different, but like our ur dot r hat thing, that is, sorry, u vector dot r hat thing, that is ur everywhere, right? So you don't have to, you know worry about that. You can just do ur, right? So this like del cross, okay, what I'm saying, right? Del cross u. So this thing, it's radial component that out with dr. Oh, sorry, that out with dA, right? Yeah, well, the sum of that thing. So it's the same as if you just, summed up all of these guys. Del cross u, the radial component only, that times the area. So that times dA, and then you integrate that guy, which would be the same thing as just the radial component of this guy, because it's like a small surface, so it's approximately the same. So just this guy is the radial component, and that times the area. But the area is just this thing, dz r d theta, and the radial component, for getting that, just dot with r hat. And yeah, you could argue that this thing is dA vector, so then it's not such a big problem to, like have the radial component everywhere and worry that you might get some other dot product over there. But fine, still what we get is this thing, del cross u dot dz r d theta and r hat, right? This is our dA vector if you want, and this is that thing. So you already know how curl is calculated, right? It's just the line integral upon the area, or you could say that the curl dotted with our area vector, that's equal to the line integral, right? For a small area, that is. So this is actually what we are doing. Just, the curl dotted with our area vector, and that's equal to this line integral. So we'll start doing this line integral now. So first, move along this r d theta thing. We only care about the theta component of our field, because every other component, well, in the dot product, it just cancels. So yeah, just got this thing, u sub theta of z. So what does this mean? That is, it's evaluated at this line where z coordinate is z. That was obvious. Whatever, it's just z. So u theta at z, and of course it's changing, like at different points you have different u theta, because z, although it's constant, the r and theta thing, those are actually changing, right? Especially not r is not changing, theta is changing. So because of that, u theta is changing, but then the difference, so take a point over here, take a point over there, the corresponding point, of course, take a difference of our u vector things, that difference is kind of constant once again. So if you don't do it very formally and kind of let it be, then fine. It's just got u sub theta at z, and that terms of this length r d theta, and then for this you also need this. Where did that go? Right, this one, minus u sub theta z plus dz r d theta. So that's for this path, right? See, I told you that the difference remains almost constant. So if you assume that this thing actually like is it's actually a constant throughout this length, then too it's okay. You're not going to get any wrong result. It's still the same thing because in the end it's the difference that matters, right? So yeah, this difference, although it's in the opposite sign, so this should be positive over here, this should be negative, so just take a negative common, and then the difference would just be partial u theta upon partial z times dz thing. So that's what this thing is, and then r d theta that was there already. Similarly, you got these two paths. So for that, you have this thing, uz theta plus theta dz. That's for this path, and then for this path, you have this, right? Once again, the difference is what matters. So you just got partial u theta upon partial theta d theta. This difference stays the constant for like throughout these two paths, right? As you move up in this path as well as in that path simultaneously, right? You could say so. Yeah, what was I going to say? Yeah, right. This difference remains kind of constant, so you can just write like that, and then divide by our area. The magnitude, of course, we don't want to divide by the vector. That would be insane. Just divide by this area, so you get this thing. Partial uz upon r partial theta minus partial u theta upon partial z. That's the radial component of our curl. Similarly, you can figure out what are the other two components. So along theta hat and along z hat, right? Um, I think along z hat it's kind of more complicated, but still it's actually doable. This length is more than this length, right? This length is more by dr d theta. You have to take that into account because that will give you an extra term. This u theta upon r comes from this fact, and once you do all that, you will basically get this. So the z component is just u theta upon r plus partial u theta upon partial r minus partial u r upon r partial theta. So you got all that. Now just put that, combine that basically, right? So this times r hat and this times of theta hat, this times of z hat, add these up. That's our curl. That's our del cross u. Of course, I didn't do that because why would I? It just requires more space, right? Okay, now all of this is done. So now I can actually finally explain what I was going to say when I said that apart from this term, this would be as if you just did this directly. What do I mean by that? So you can write the del operator in our cylindrical coordinates like this thing. So it's r hat partial on partial r plus z hat partial on partial z plus 1 upon r theta hat partial on partial theta. But the way you will apply this del operator on some vector or some scalar is that you have to first apply the partial derivative on whatever you are applying this on, and then multiply in quotes. What that means is like if you're using like del cross over there, so you're taking a curve, then you have to do the cross product after you apply the partial derivative, right? So you do partial and partial r first, and then you will do r hat cross with whatever vector you'll get, right? Yeah. So the order of operation does matter over here. Okay. Yeah. And although it will be like all of this in bracket, and there's a cross over here, you could think that first you will have to cross, and then like first you have to multiply cross product, and then you will have to take a derivative. No, that's not the way it should be. Actually, when we say del cross, what we mean is like r hat cross that as an operation, and then just before that we have partial and partial r, right? That's the way we should interpret this thing, not as all of this and then a cross over here, right? That's not the way it should be. Okay. So that's why first apply the partial derivative, then multiply, okay, with the unit vectors, and not in the opposite way. And if you did it in the opposite way, then what you get is something like this, right? Yeah, you won't get this term if you just did it like that, right? So del dot u, our del would basically be this thing, and our u vector can be written as u r hat plus u theta hat plus u z hat. Then if you multiply it first, you just get like r hat dot r hat, that's like 1, and then every other thing just has the dot to be equal to 0. So like the first thing just gives us partial and partial r of ur, right? Then the next one would give like partial and partial z of uz, and the next one would give 1 upon r partial upon partial theta of u theta, right? If we multiply it first and then the partial differentiation. So you should not do that, right? You should do the opposite, because if you did that, you won't get this fourth um, term that you should actually get, right? Okay, and doing it like that, you can actually construct our divergence and curl without the full derivation, right? So it's kind of like like a mnemonic to construct these when you want to, although that's not how these should be constructed. Like it's not a proof. It's not a proof that this is the formula. No, 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 no. It doesn't prove that, right? It's just a mnemonic. Remember it. Okay. Uh, yeah. So I have an example over here. So this thing theta hat upon r partial theta cross u theta theta hat. First, you'll do the differentiation, right? So differentiate theta hat as well, because that's a variable vector now. Like x hat, y hat, z hat would be constant vectors, but theta hat is not. It's changing depending on where you are. It depends on your position. So our partial theta of theta hat, you have to consider that as well. And of course, that would just be using a bit of complex numbers and stuff. That would just be negative r hat, right? So yeah, this would basically be partial u theta upon partial theta hat, because first component's derivative, then the second component's derivative, this remains the same. This guy's derivative is just negative r hat, so like negative u theta r hat, and then do the cross product. So finally, you just get this thing u theta upon r z hat. Awesome. So this was for cylindrical coordinates. We also have some like similar formulae for spherical coordinates, although they are much more ugly, and so is spherical coordinates. Like so are they in general, because you get more trigonometry everywhere. So yeah, I don't usually like using spherical coordinates, but then sometimes you don't want this distance, you want this distance, right? That is of more important, like that's more important sometimes. This is not so important. Then you just use spherical coordinates, which is problematic for me because I didn't derive this thing and I don't want to be using this. But fine, whatever, we'll still start. Okay. Right, where was I? Oh, this is not what I wanted to do. I wanted to do the problems first. Right, this is where it starts, right? Where's the first problem? Oh, I don't want all that. Just give me a problem first. This is an example, not what I want. Alright, find the formulas for r, theta, and phi in terms of x, y, z. The inverse, in other words, of equation 1.62. Okay. Right. I think phi would be the easiest, right? Yeah. Yeah, I think so. So like, how do I even explain this? Whatever. Just got this thing, right? R x equal to r. Wait, what was this one again? R sine theta cosine phi, and this is equal to r. You just copy this, in fact. Why even bother to write that down? So what you can do, just divide these two equations. You get like x upon y, that is equal to quad phi. So like tan phi is equal to y upon x. So phi would just be tan inverse of y upon x. Wait. Well, this has a bad range. I don't want that range. I want this to go from 0 to 2 pi, right? Yeah, that's what it should be doing. It should be going from 0 to 2 pi. So I guess that's not the way to be doing it. Okay. So basically phi is an angle such that x upon square root of x square plus y square, that's equal to cosine of phi, and y upon square root of x square plus y square is equal to sine of phi. How do you get the precise angle from this though? Like cosine inverse is in 0 to pi and sine inverse is in negative pi upon 2 to pi upon 2. That is not what I want. I don't want just half of the circle. I want the full circle, right? Where's the third quadrant? How do I get to the third quadrant now? This is not going to work. Yeah, it's definitely not going to work like this. Uh, I guess you could use complex numbers, right? So 5 would be like the argument. Wait, argument goes from 0 to 2 pi, right? Or does it go from negative pi to pi? I don't know. I'm going to define like the angle going from 0 to 2 pi. So the argument of this complex number, x plus iy. Easy. Yeah. So, you know, the way we define cosine inverse and sine inverse, phi probably won't be that easy to get, right? Like just feed these functions into a computer and that spits out some nonsense. It's not what we want. We want it to spit out exactly what we want, right? Something in 0 to 2 pi. We shouldn't give like negative 30 degree. That's not what we want. Okay, so that's how you get phi. That's a formula. Not exactly, but that is a method though. So phi is the angle such that this happens. Yeah, end of the story. There is no such function, like elementary function, that could give me phi directly. You just have to do it by yourself. Okay, there should be really just a function that takes in two inputs and gives out one output, like this function, you know. Just like it's from 0 to 2 pi. It has to take these two inputs, x and y, and give out one output. Why don't we have more functions like these in trigonometry instead of having like cosine inverse and sine inverse? We should really have two input functions, right? Whatever. So that's how we get phi. Next you want to get theta. Okay. So of course you can like x squared plus y squared. There you go. You just got r squared sine square theta in that way. Z square is just r squared cosine square theta. I think I'm starting to understand. Well, theta goes from 0 to pi. And z is basically this thing. Ah, right, of course. It's just z upon r. R is just this thing, square root of x squared plus y squared plus z squared. And cosine inverse of that guy. Now, this thing does lie in the range that I want this to be in. Yeah, awesome. So that's what theta will be. That is like, yeah, that explains it. Okay, this is the formula we are looking for, right? Okay, then for r, well, r is just square root of x squared plus y squared plus z squared. No big deal. Okay, problem 1.37. Express the unit vectors r hat, theta hat, phi hat in terms of x hat. That is derive equation 1.64. Check. Right, so I'm gonna just explain what's going on over here. Well, first of all, let's start with the easiest one. Like, okay, r hat. Okay, r hat, which is it's for spherical coordinates, right? It's not for, yeah, like you got two angles, spherical coordinate. So r hat is this vector. First of all, what is r vector? This is x, y. I don't think you should be using that. Okay, what's right? Okay, you got these x, y, z things. Well, just x hat plus y hat plus z hat is what r vector will be. Just divide by r, and there you go. That's the thing. So yeah, like just got sine theta cosine phi x hat plus sine phi. Sorry, yeah, like sine phi sine theta y hat, which is exactly what's going on. Plus cosine theta z hat. Easy as that, right? That's what r hat would be. Okay, you can also view it like this thing. It's sine theta times the unit vector, which is in the xy plane, right? So just the projection of this thing on the xy plane of r hat, yeah, plus cosine theta, and then you got z hat over there. I shouldn't say the projection. I should say the unit vector along the projection. Whatever. That's what r hat is. Then what's theta hat? So theta hat is like 90-degree clockwise of r hat. So if this is like the real axis and this is like this unit vector, that's our imaginary axis, yeah, then this thing is just iota times whatever this vector would be as a complex number, of course. So this as a complex number would just be cosine theta plus I sine theta, right? Then this thing would be iota times that guy, which is I cosine theta minus sine theta, right? And then minus sine theta times 1, well, yeah, the real part, that's just something along the z hat. So minus sine theta z hat. and the imaginary part, that's along this, the thing, right? This vector, this projection on xy plane stuff. You get the thing. So it will be this thing, right? And then lastly, you have to define phi hat. Oh, that's the easiest thing, in fact, because right, yeah, it's only the xy plane that we have to be looking for in that case. You don't have any z component because it's completely xy plane. You just want to go from there to there. Easy as that, right? And of course, depends on where you are actually. Oh shit, I think this is not where it's supposed to be. It's supposed to be over here. Sorry. Yeah, that's where it's supposed to be. Okay, who cares? Right, because this is actually the point of our interest. Fine. Yeah, what is it going to do about this? Right, what's phi hat going to be? So, we are at this position, and then you want to go in that direction, right? Exactly. This vector that we're talking about, this is our, the xy projection of our position vector. That's what this thing is. I think something's going weird over here because that's clearly not the r vector. Why did I draw it like that? I don't get it. Something must be wrong over here. This should be our r vector, like going from there to this point. Okay, cool. And this would be, I don't know what this thing is. This is our complete radius, like the length of the radius, which is r. It's not r vector, no. R vector would be going from here to here, which is also of length r. This is our z vector, which is like just z itself, yeah, but in the z hat direction. So this is of course r cosine theta. Then this length is r sine theta, and then you're making this vector rotate about our z-axis by phi to get this vector, which is the xy projection of our um, position vector, which is basically what this unit vector is for, right? This vector is in that direction, right? Then it's very obvious that you just have to rotate it anti-clockwise as seen from above by 90 degrees, and then you'll get this vector, right? To do that, of course, think of it as a complex number multiplied by iota. What you get is this thing. Okay. See, I already told you, like, I don't like spherical coordinates. I didn't even put enough effort to draw this picture, but whatever. Okay, instead of the boring derivation, I mean, we already did this, right? We already discussed about this thing. From the 1.37, we did that. Okay, check your answers several ways. R dot r hat equal to 1. Is it equal to 1? Well, of course it is. Any vector has that property. Why do you ask me this? I don't understand. What's even the point of asking this question? Okay, then you got theta hat dot phi hat equal to 0. This sorted with this guy is just okay. Okay, you got negative sine phi cosine phi. That's sine phi cosine phi. That cancels out. And there's no z component, so 0 times sine phi, sine theta. Sorry, that's 0. So yes, that is correct. Oh, okay. The length of this thing should be 1. That's what they're saying. Well, this guy's length, right? We know it's going to be 1. This is a unit vector. This is another unit vector, right? Based on z hat and this unit vector, right? Okay. Also, what else do you want? R hat cross. I'm not going to do that. It's just a lot of work. Also, work out the inverse formulas giving x hat, y hat, z hat in terms of r hat, theta hat, phi hat. Are you serious? I don't want to be doing that. Okay, and theta and phi. Wow. So you want me to solve this to get x hat, y hat, z hat? Seriously? Why? God. Okay, how do I start? Guess you can get x hat using this vector. Well, okay, that vector is not useful in the end. This is going to be a very long question, right? How am I supposed to get this? It's like a linear equation in three variables, and this is just stupid, isn't it? Exactly, it's just very stupid, in fact. It's like we have to figure out the inverse of a matrix and then multiply that matrix. What not? It's just not worth it. Definitely not worth it. And what would I even do after getting that, right? We already start at the Cartesian coordinate system everywhere, right? We go to the spherical or polar coordinate system if we want. It's not a necessity. So there's no point to go from spherical to Cartesian. Yeah, there's no point in doing that. And just for the unit vectors, well, definitely not. I mean, this is already good enough. You know, if you want to go to, you want to go from spherical to Cartesian, this is good enough. There's no need for converting unit vectors. Okay, so I just won't do this. It's just a lot of work. I know how to do it. Just have to solve these three equations. Like think of x hat, y hat, z hat as our variables. These quantities are like constants. You can think of it like that, right? And then solve it in terms of r hat, theta hat, and z and phi hat. You know, instead of thinking these as like vectors, you can think of these as like algebraic quantities, right? Yeah, just solve the linear equation system. There you go. You got your answer. Okay. Then 1.38. Check the divergence theorem for the function v. What is this? 1. Okay. v1 equal to r squared r hat. Using a volume. What? Using a volume, the sphere of radius r centered at the origin. Okay. Whatever. Divergence theorem for this function. Fine. So what does the divergence theorem say? Our flux that's equal to the, yeah, the flux is equal to the volume integral of the divergence. Well, what's the divergence of this guy though? We already got divergence in this, right? So we got this thing. There is no theta hat or phi hat component for our v, which means, yeah, most of these terms are going to be zeros. Like this is going to be zero, this is going to be zero, this is also zero, and these two terms survive. Okay, so 2u_r upon r, that's just sorry, what is going to do? Yeah, 2u_r upon r. ur is just r squared, so 2r. Okay, 2r plus, well, this derivative is 2r once again. So just get 4r. 4r is our divergence. 4r r hat, I should say. Well, okay, this is a divergence we're talking about, not the gradient or something. So yeah, 4r, just the number itself. So that's our divergence. So you just want to integrate this for the complete volume, which is our sphere in this case, right? We just do this for a sphere. That's what they're saying too. Use the volume as a sphere of radius r centered at the origin, of course. So we want to integrate. But okay, you know what? Let's just think of our dv element as, you know, not the actual dv element used for the triple integral, but instead just thin shell. So the volume of that thing is just like 4 pi r squared dr. And our function is 2r, no wait, 4r. Yeah, so 4r, 4 pi r squared dr. Yeah, that's the one integrand. Just integrate this thing from r equal to 0 to capital R, and we are thinking, is this actually equal to the flux, which is yeah, just 4 pi capital R. So that's our area that comes of this radial component, which is just 4 pi r power 4. Yeah, this is like what you got, 16 pi r power 3 dr. It's like 16 pi r power 4 capital R power 4 upon 4, which is just this thing. Yes, it's the same thing. Yeah, of course it's only the same thing. Believe in maths. Okay, do the same for v2, which is 1 upon r squared. Okay, whatever. Once again, what's the divergence in this case? So you got 2u_r upon r is like just 2 upon r cubed, and then the differentiation is -1, -2 upon r cubed. Oh, that's 0. Okay, cool. Hey, I know where this is heading. It's once again that, oh come on, it's like representing a field from a point charge. I get that, and it's discontinuous at the origin. So, the divergence does not make sense near the origin. So like, how do you expect to integrate this thing? Uh, I don't know. I don't know. How am I supposed to do this? Everyone else is zero, and then at the origin it's different, right? We know it's different. It's going to infinity suddenly, and it's a different function. Okay, so we can't just say that this thing is going to be zero, right? The volume integral is not just zero. It's something, but I don't know what exactly it is. Okay, if the answer suffices, you look back at problem 1.16. Yeah, I think that's the problem where we basically figured out that this thing is discontinuous at our origin, or like the divergence is going to infinity at our origin, or whatever. So, yeah, like that's the infinity times zero case, isn't it? Another indeterminate case. Yeah, right. I guess we'll have to go to the definition of divergence in that case. It is flux upon volume in starting, right? That's the way we defined it. So then it would make sense that this integral, right, that this divergence theorem is true all the time. So it would still be true. It's just that both sides, not both sides actually, just the left hand side, it contains some questionable stuff. Yeah, the right hand side is just a flux. So that thing is like what? You got 4 pi r squared times 1 upon r, which is 4 pi. So the flux is 4 pi. Left hand side should also be 4 pi. Okay, I guess we just have to say that we don't know what's going on over there, right? Or that maths breaks down because discontinuity. Whatever, just move on. Let's just move on now. Okay, compute the divergence of this function be equal to r cosine theta r hat plus. Right, so it's in the spherical coordinates. You will have to use, what do you want by the way? The divergence. So this thing. Oh, this is going to be hard. Fine. This volume is the inverted hemisphere spherical ball of radius r, like this thing. Then, yeah, fine. Any nice property this thing has? R cosine theta, R sine theta. It's in the r hand direction. Hmm. That's weird. Yeah, whatever. Just start. So this thing, right? 2 r upon r, that would just be 2 cosine theta. So 2 cosine theta, and the derivative of this thing is equal to r, of course. The cosine theta is dependent on theta only. So all you get is like cosine theta once again. It's just 3 cosine theta. Okay. And this looks like, yeah, it's a nice function. It doesn't have discontinuity anywhere, right? Cool. So 3 cosine theta. Uh, okay. Plus, other term is partial u theta upon r partial theta, first of all. Okay. So 1 upon r and then the derivative, which is theta, of course. So you got r cosine theta upon r, just cosine theta once again. Okay. Plus, this one is u theta cosine theta upon r sine theta. Well, r sin theta is okay. That's getting cancelled. You got u theta. Oh yeah, that got cancelled. Just cosine theta once again. Wow, that's weird. Okay, then you have partial u phi upon r sine theta partial phi. So this guy's derivative with respect to phi. Okay, it should just be negative r sine theta sine phi. That upon r sine theta is just negative sine phi, of course. Well, that was something. Right. Yeah, that's the thing, of course. Uh, Awesome. So what you get, you just get like 5 cosine theta minus sine phi. Okay, that's the divergence of this thing. Check the divergence theorem for this function. So what's the volume integral of this thing over this hemisphere? Okay, this is going to be hard, isn't it? So it's not depending on our radius at all, right? Very interesting. It does not depend on the radius. Wait. I guess at this point, triple integral is the best way to be going, right? Yeah. So our dv element, what was it once again? It was just, um, wait, what was our dv element once again? It was like this thing. This is your r, then you got dr over there. Then you change your theta a bit. This thing is r d theta. And then you change your phi. This length is just whatever this length is, which is just r sine theta. And then you got d phi. That's what this length is. So this cube has the volume of r square sine theta d theta d phi dr. So this dv thing times our divergence, which is just this crazy stuff. And you wanna, okay, so first of all, what's the integration of r squared going r squared dr going from 0 to capital R? Because that's something we can actually take out, right? Right. That's just gonna be like r cube upon 3, right? Okay, and then you have this double integral. So your theta is going from 0 to pi upon 2. And then you got this thing phi cosine theta minus sine phi. And you got d theta. Oh, there's also this thing, this sine theta over there. So you have to put that in as well. Cosine theta, sine theta. Okay. Sine phi, sine theta. That's interesting. You got d theta over there and you got d phi. The phi is going from 0 to 2 pi. Nice. First we'll have to integrate this thing, which is like phi upon 2 sine of 2 theta, right? So like sine upon 2 theta. So you know what, just phi upon 4 sine of 2 theta d 2 theta going from 0 to pi. So sine theta going from, yeah, right, 2 theta goes from 0 to pi. So that integral will just be 2 in fact. Yes, I'm sure of that. Just this times 2. It's like 5 upon 2 is what this will be. Yes, I think that is the case. So this will just not be 5 upon 2 minus, well, this guy. So sine theta going from 0 to pi upon 2 is just 1. So yeah, just minus sine phi over there. So this is what this integral will be. And then you got d phi, this integration from 0 to 2 pi of this guy, and you got r cube upon 3. Okay. So sine phi going from 0 to 2 pi, well, we can see what's going to happen. It's like the imaginary component of, the complex number e power I phi or something, and then like by physics, that when all of these are just radially pointing outward, like, yeah, by symmetry, it's going to cancel out or something. So in the end, this integral of this guy, that's just 0. Yeah, that is 0, of course. Awesome. So what you get is like r cube upon 3 times this guy's integral, which is just 5 upon 2 times 2 pi. So just 5 pi. Yes, that's the thing. So you got 5 pi upon 3 r cube, right? That's what this volume integral will be. What's the flux? Wow, this is not looking good, Definitely not looking good. Okay, what's the flux? This thing is the divergence, right? What our function was is this thing, of course. Okay, your r is, okay, you just have to multiply by the area element. This is getting hard. Flux. Oh, that's going to be hard. Yes. We'll also have to take this surface in there as well. Okay. That is only pointing in the z direction. There's r hat over there. Okay, our theta hat is in that direction. That doesn't actually matter here. So our phi hat. Wait, no, phi hat is the one going in this direction, right? Yeah. And theta is going from 0 to pi. Right. So, oh yeah, okay. So on the xy plane, your theta hat is the same as, I had to the opposite actually. Yeah, the opposite of your z hat, right? Okay, let's try it out. So this is the volume integral. We'll try out the flux now. So first, this surface, it's once again a double integral. but now you have to think of the dA element. So it's like at distance r or capital R, whatever. This thing is about r d theta, and this element is your r sine theta d phi. So this area element dA is just, r squared sine theta d theta d phi, right? So multiply this with, oh yeah, and the area element is in the r hat direction. So you just have to do like r cosine theta, this guy. Yeah, that makes sense. So what you get is like r cube sine theta cosine theta d theta d phi, and you want to integrate this thing from theta is equal to like 0 to pi upon 2, of course, right? Yeah, I think so. And other integrals going from 0 to 2 pi. Okay, fine. So right, we already did this kind of thing before, didn't we? Yeah, it's like what, r cube upon 2, just pull that to the front. R cube upon 2, then you got sine of 2 theta, then r cube upon 4 sine of 2 theta d2 theta. That's going from 0 to pi. The integral will just be 2 in that case, because yeah, sure. So r cube upon 4 times 2 is just r cube upon 2. So you got r cube upon 2 sorry, 0 to 2 pi, and just got d phi over there, which, yeah, just 2 pi over there. So what do you guys like, pi r cubed? Huh. Okay, I guess. Hey, why is there a 3 over here? Is that correct? I think it was. It was from the integration of r squared. Yes. Okay, so you got pi r cubed from this hemisphere. And what about from this base? So it's only the z hat direction that we should be thinking about. That's where the area vector is pointing to. So just basically this guy, and you want to integrate this. Okay, what's our dA element once again? Now our theta does not matter in the end, it's just phi that we are talking about. So we have pi r cubed, and what about this one? Yeah, our area element is just r d phi dr. Okay, and that's in the z hat direction. Of course, this thing in the phi hat direction is just pointing downwards. It's just negative or something. Oh god. Wait, if this is this is pointing in the, it should be the negative theta hat. Wait. Something's not being correct about this. When we try to figure out the flux, like we take the area element, we take the area vectors pointing outward every time, right? So over here, the area vector is also pointing in the, oh yeah, it's also pointing in a theta hat direction. It's pointing in the negative z hat direction, right? That's where our area vector is pointing to. So yeah, no need for this negative. Our area vector is just this thing, and then you got the no d over there. What you got is like this thing, theta hat, not z hat, but theta hat. So yeah, then dot this vector with that. Of course, this thing. You don't want that. You instead want this over there, r sine theta. Okay, so it's like, oh, it's a double integral, of course. So r going from 0 to capital R, and theta going from 0 to, is that theta? Wait, it's r sine theta. That should be 0. God. Wait. Oh no, okay, theta is actually at 90 degree in this case, not 0. Sorry. So this would just be 1 in that case. So you got r squared dr, and then you got d phi over there. Look good. Phi is going from 0 to 2 pi, I think. So you just got like 2 pi, and then you got r cube upon 3. So you got 2/3 plus 1 is 5/3. Yes, this is actually correct. This is equal to this plus that. Yes, the volume integral is equal to the flux. Cool. So it does work. Next, you want to compute the gradient and Laplacian of the function. This function. Check the Laplacian by converting t to Cartesian coordinates and using equation 1.4 to test the gradient theorem for the function using paths shown. Okay, once again, just a lot of check this, check that. I don't want to do any of it. Cylindrical coordinates. Once again, what is the function though? T is equal to this r cosine theta plus sine. Once again, in spherical coordinates it's given, and you want to figure out the gradient and Laplacian of this guy. Easily doable, right? Yeah, I mean, we already know the equations. Oh, the Laplacian, we don't know the equation. I mean, we do have it. They already gave us a thing, but why? Why do you want the Laplacian of this guy? Well, whatever. We can definitely easily figure out the gradient. And what after that? Check the Laplacian by converting T to Cartesian coordinates. Oh god, no, that is not worth it. Why should we? Okay. Test the gradient theorem for this function using the path shown in figure 1.41. Nope, not doing this. It's just a lot of work. There's nothing enlightening over here. Okay, then you got cylindrical coordinates. Okay. I mean, we already did this, right? We already did this in very great detail. Express the cylindrical unit vector in terms of x hat, y hat, z hat. And z hat is z hat, of course. What about so s hat? I think s is what they are calling the r, right? So this r, where did that go? Right, this r is what they're calling s. I think sometimes people call it rho as well, or whatever. Of course, you just have r hat is equal to cosine theta x hat plus sine theta y hat, and theta hat is equal to, so I have to times this guy, right? Just negative sine theta x hat cosine theta y hat. Easy as that, right? Easy as complex numbers. Okay, what was I doing? Oh yeah, and they want it in their notation. So this would be like phi hat is equal to this. Everywhere instead of theta, just put phi. Instead of r, um, just put s. Yeah. Invert your formulas to get x hat, y hat. Are you serious? Okay, at least this one is doable because it's like, yeah, it's like this thing. R hat plus I theta hat is equal to, wait. I think that's not what we should be doing. Right, do it like this thing. R hat is equal to, this looks weird, but trust me, I know what I'm doing. I'm using complex number for this thing. E power I theta, and theta hat is equal to I e power I theta. Okay. Now you want to get x and like x hat and y hat somehow, right? So how do we get that? Wait a second. Think about it. I think, okay, what do you want, like 1 on one side? Huh. Right, that's not the way to be doing. Oh yeah, okay, I understand what's going on. This won't work like that. Fine. You can just do like e power negative I theta over there, and then that will work. Sure. So there's iota involved and whatnot. Uh, I mean, it's not that bad. I guess we can do it. We can just, do this thing. R hat e power negative I theta, that's equal to 1, and 1 in our context of complex numbers is like x hat. So what we really mean is like x hat is equal to this thing. So first you just want cosine theta times this guy. So you got, oh come on, seriously, right? So you got cosine theta r hat, and then there's like negative iota sine theta r hat. So iota does is, okay, iota applied to r hat is just theta hat, of course. So just a negative theta hat sine theta. So that is our x hat. And you also want to get y hat somehow. How do you get that though? Like this, iota r hat e power e negative I theta, right? So like this vector, uh, iota applied on that. So yeah, iota r hat is just theta hat. So you got that over there. It's theta hat cosine theta. And this with iota, well, this is already iota. Wait, no. Iota applied on theta hat is just negative r hat, right? Yeah. This would just be like r hat sine theta. Alright, plus theta hat cosine theta. That's what y hat will be. So there you go. You got x hat and y hat in terms of r hat and theta hat. Nice. Of course, you can do like, solve this equation, multiply by cosine theta over there, sine theta over there, then subtract these guys. This will become like x hat. This would just cancel out. So, cosine square plus sine square is just 1. So that's why this is just x hat. This would cancel out because negative and positive. And you will get x hat is equal to this guy. Easy as that. Or you could do this thing. Both are the same. Right? What I did basically is just like applied an inverse rotation matrix. Okay, let's not go into those details. Right. What do you have? Laplacian. Okay. Wait, what was it doing? Oh yeah, I was doing problems. Express cylindrical unit vector in terms of x hat, y hat, z hat, and invert your formula to get x hat, y hat, z hat in terms of this guy's whatever. Then you got 1.42. Find the divergence of the function, this function. Okay. So this is in cylindrical coordinates. Easy. Let's do it. So you got ur upon r, which is this thing. Instead of using s, they should have used r, right? That's what usually people do, right? That's what normal people would do. Okay. So differentiate this to r or s in this case. What you will get is, oh, not yet. Actually, just divide this by r. Sorry. So this will just be like 2 plus sine square phi. Okay, that's our ur upon r thing. Then you got plus partial ur upon partial r, which in this case is actually the same thing. So just 2 times of this guy. Awesome. And then plus partial u theta upon r partial theta. So, just differentiate it with respect to phi in this case. Whatever. It should just be. This is like what? It's just r upon 2 sine of 2 theta, right? That's what this thing basically is. Differentiate that with respect to theta. That should just be r cosine of 2 theta, I think. Right? And then, divide by r, of course. So you just get like cosine 2 theta. No phi required. It's supposed to be theta over there. So 2 theta. Awesome. Okay, that's the other part. And then finally just got partial uz upon partial z, which is just 3. So here you go. That's our divergence. 7 plus 2 sine square theta plus sine of 2 theta. Wait, you can actually write like, if you can write like 1 minus 2 sine square theta. Guess what this cancels? Just get 8. 8 is the divergence of this thing. Okay, test the divergence theorem for this function using the quarter circle, radius 2, height 5, should figure 1.43. Where's that? So this thing, okay. Quarter cylinder. Wow, seriously. Fine. Okay, let's try to do it. This is the function. That's what I was. It's 8 constantly. What's the volume of this guy? So this is the radius. What? Radius 2, height 5. It's like 1/4 pi r squared. R squared is just 4. So pi. Yeah, pi is the space. Height is 5. 5 pi times 8 is just 40 pi. 40 pi is our volume integral. And let's see what our flux will be. So first we'll do these plane surfaces. Right. This surface is pointing in y hat, right? Which, wait a second, for all the points in this thing, this is actually the same thing as theta hat, I think. Yeah, just r hat and then rotate counterclockwise. It is actually just theta hat. So no, but we want it to be outward. It should be negative theta hat. Fine. So negative theta hat. What's the function? Okay, what's the component in theta hat or phi hat or whatever? It's just negative. Once again, like negative r upon 2 sine of 2 theta, right? That's what it will be. So yeah, just integrate this guy throughout this surface. Oh god. Good thing it's not a function of z, right? First just integrate for a strip, right? So your, wait a second. Your r is there. Okay, so r is variable throughout the surface, and your phi or theta, that's actually constant. Your theta in this case is just, it's just 3 pi upon 2, I think. Yeah, right. So 2 theta is just 3 pi sine of, oh, that's 0. Awesome. That's is 0. Somehow it turns out to be 0. Okay, like cosine theta is 0 at that point, so it's nice. Well, that's 0. Awesome. And that means the flux through this guy is 0. And similarly, flux through this guy will be 0 because cosine, that's not 0 actually, sine is 0 in this case, right? Over here. And this is pointing in, once again, just in, theta hat. Yeah, right. So these two surfaces don't give any flux. What about these two surfaces? Pointing in z hat and negative z hat respectively. Okay, so you got 3z over there. That's okay. 3z times whatever this area is. You already know what this area is actually. It's just pi. So pi times this value is just, so over here is just 0 of course, and over here it will be, but what's this height is just 5, so like 3 times of 5, 15 times pi, 15 pi, so 15 pi, and plus now yeah, this integral, so this surface. Okay, so only the radial component is what matters in this case. So you got x 2 plus sine squared phi. Okay, s is like r over there. Okay, r and then 2 plus sine squared theta. Okay, cool. Right, so for a function we also want our dA element, which would be just r d theta times dz, and this integration is going from, like, okay, r is constant, r is just equal to 2 everywhere, so like this integrand, what it actually is just you know 4. Okay, okay, yeah, I think that is the thing, or you could split this, whatever. It's just 4 times 2 plus sine squared theta d theta dz, and yeah, your theta is going from 0 to pi upon 2, I guess. Yes, I think that's correct. It is going from 0 to pi upon 2. Awesome. Hey, okay, wait, okay. For this surface, theta was not 3 pi upon 2, it was actually 0. Oh, that's still 0. And then over here it was pi upon 2 because this is x, this is y. I thought this was x and this was y, but whatever. It's still 0 in any case. Okay, cool. What is it going to do? Right. This thing. Yes, yes, okay. The other integral for dz, right? It's going from 0 to 5. Awesome. So what do you get? First you got like 8 plus 4 sine square theta, which you can add like 8 plus it's like what? So 2 times cosine is just 2 times of 1 minus cosine of 2 theta, of course, which is just 10 minus 2 cosine of 2 theta, that times of d theta, 10 d theta, the integration of that guy from 0 to pi upon just like 5 pi, of course, minus this integration, so just, like cosine 2 theta and d2 theta going from 0 to pi in that case, right? 2 theta goes from 0 to pi, of course. So it's cosine, and that's, oh, that's 0. Awesome. This whole integral will just be 0. So you just got this thing. This integral, you can remove it and just say 5 pi. And you got this thing. Awesome. So you get 25 pi, it seems. Add these. Yeah, you get 40. Awesome. So divergence theorem, it still works. Okay. Finally, you have to find the curl of our vector. Okay. V is equal to, right? Let's look those formulas up. Right, this is the thing. So the radial component is partial u z upon r partial theta minus partial u theta upon partial z. Fine. Uh, this is our function. You know what? It's just a lot of work and not useful in the end. So why should we do it? Right. Find the curl of v. As if that's going to do anything. Then the next section is the Dirac delta function. I think I read a bit of this before starting on this video, but still I'm not going to do it on this video. I'll do it in a other video. Okay. Yeah, like basically the question that we got for the 1 upon r square r hat thing, like why is the divergence theorem not quote unquote working? Yeah, that will be resolved in this thing. Actually, it's still working. It's just that we have to define a new function so that, you know, like the divergence actually makes sense, right? At our 0 comma 0 point, divergence should make sense to actually apply the divergence theorem. So um, for that, we'll actually define a completely new function, which is going to infinity. I know it's crazy, but that's the way this function is defined with the finite area and infinite value. Fine. So we'll do this in the next video. See you guys in the next video. Bye.